the last module we were discussing rectangular waveguides and we discussed how to derive expressions for transverse magnetic modes. If you recall what transverse magnetic modes are, these are the modes for which the magnetic fields lie entirely in the plane that is perpendicular to the direction of propagation. Because we have chosen Z as the direction of propagation, this statement TM mode simply means that there is no Hz component. So all the magnetic field components that we would find will be Hx and Hy. The corresponding longitudinal electric field component along the direction of propagation must not be equal to 0. So which means that you will have full electric field having components Ex, Ey and Ez, whereas for the transverse magnetic mode Hz component will be equal to 0. By cleverly manipulating Maxwell's equations, we were actually able to write down Hx and Hy, Ex and Ey, which are called as transverse component. Transverse means perpendicular. Okay, so these transverse components in terms of longitudinal. Longitudinal is along the direction of propagation. So we were able to express everything in terms of some functions of Ez. Okay, of course that function will also include Hz, but for the transverse magnetic modes Hz is equal to 0 and these components are functions of Ez alone. This was our first step, right, in obtaining the solution for the transverse magnetic modes. The second step that we did was to write down Helmholtz equation for Ez. Right. So we wrote down the Helmholtz equation. This Helmholtz equation was solved by a technique called as variable separable method, which allowed us to express Ez in terms of x of x, y of x. Of course, we will assume that all the fields are propagating as e to the power minus j beta z for a lossless waveguide, or as in general e power minus gamma z for a lossy waveguide. Okay. So this was the Helmholtz equation. This is the form of the z dependence that we had assumed, and once we wrote down the Helmholtz equation, the third step was to essentially apply boundary conditions, right. So we applied boundary conditions by realizing that the tangential electric field must vanish on the perfectly conducting walls of the waveguide, and from there we obtained expressions for Ex and Ey. So from the boundary conditions we kind of understood how Ez must vary, and we found that Ez must vary as some sign. There is of course some proportionality constants, but that is not really important for us at this point. So as a function of x and y, it has to be sine of m pi x n pi y by b. Finally, I would call this as some 3 prime. This relationship is something that will give us the relationship between the magnetic field and the surface currents that should exist. Remember, the tangential magnetic fields must be discontinuous by an amount of surface current. So whenever there is a possibility for surface current to be present, then magnetic field component will converge to that boundary condition. So the surface current that should be there on the walls is given by the normal component times H, where the normal component An is actually directed from the, this is the waveguide, from the wall into the waveguide. So this is the wall of the waveguide and it would be directed along the direction into the waveguide wall. Okay. So this relationship is necessary when we want to evaluate the losses in the waveguide, or just to understand what currents need to be there in order to have the magnetic fields present there. Okay. Of course, this H will also be at the surface, that is you have to evaluate the magnetic fields at the surface so as to obtain the surface current. Okay. So what we want to observe here is that given different values of m and n, right, for every value of m and n combination there will be one solution, that is one form of Ez which would be present, right. So one solution for Ez and correspondingly for Ex, Ey, Hx and Hz. So in other words, given any combination for m and n, you would be able to find the electric fields and the magnetic fields which will satisfy Helmholtz equation, which will satisfy boundary condition, but their shapes would be slightly different depending on m and n, right. This set of components, right, for every value of m and n which has a particular shape because of x, y and z dependence is called as a mode. Mode is nothing but solution of Maxwell's equation for the waveguide along with boundary conditions. The solutions must satisfy boundary conditions in addition to satisfying the appropriate wave equation for the waveguide. Okay. So this is what a mode is, and clearly you can see that if you start giving infinite number of values for m and n, there exists an infinite number of modes, right. So what distinguishes one mode from another mode is what is the components m and n, because the form of all modes will be essentially the same, right. So if you leave out the constants out there, electric field, the z component of the electric field will go as sin m pi x by a, sin n pi y by b, and giving different values of m and n will produce different modes. So the question is, what is the lowest value of m and n? Remember, m and n must be integers, okay. So m can go from 0, 1, 2 or so on, similarly n as well, right. So these m and n are integers, and the lowest value of m and n for which the corresponding wave solution or the corresponding mode exists is called as the lowest order mode, okay. It is the lowest order mode that will propagate also with the lowest cutoff frequency. So in other words, this lowest order mode is what we call as, this has the lowest cutoff frequency, right, FCMN, and this mode, because no matter, so the moment you exceed f, the generator frequency exceeds fc, this particular mode would always be conducting, or this mode would appear inside the waveguide, and because this is the one which conducts at the least possible cutoff frequency and would always be present whenever f is greater than fc, this is called as a dominant mode, okay. So given different values of m and n, the lowest values of m and n together, for which Ez and all the other corresponding components are non-zero, is called the lowest order mode or the dominant mode, okay. So this is called as the dominant mode. Alright, let us try to find what is the dominant mode for the TM mode case, right. So in the TM mode case, the functional forms are sin m and sin n. If I put m is equal to 0, n is equal to 0 in the hope of obtaining the lowest order mode, I will not be able to obtain anything, because for m equal to 0 and n equal to 0, Ez will be 0, which also makes the total electric field, the transverse components and the magnetic field transverse components also go to 0. In fact, this condition would be true no matter whether m is equal to 0 and or n is equal to 0. Thus, the modes which are designated as Tm, Mn can never have any of these subscripts equal to 0. So these two subscripts cannot be equal to 0, neither one can be equal to 0. So what is the lowest order mode in this case? Well, clearly m is equal to 1, n is equal to 1 is the lowest order mode for TM case. So this is the lowest order mode TM11, also called as dominant mode, okay. So dominant mode for the transverse magnetic case happens to have the mode index of 1 and 1. For this mode, the electric field component Ez goes as sin pi x by a, sin pi y by b, and there is e to the power minus j beta z, okay. This is of course the phasor form of the electric field that we have written. So I should technically have written down the phasor notation for this. I have not included, just to simplify the notation. To obtain the correct expression for Ez, which is a function of x, y, z as well as time, you need to multiply this phasor by e to the power j omega t and then take the corresponding real part, okay. So when you do that one, what you get is x and y are unaffected, you get sin pi x by a, sin pi y by b, and here you get cos of omega t minus beta z. This is somewhat comforting for us, right, because there is a cosine waveform, but that is traveling. Similarly, you have sin of pi x by a, sin pi y by b, describing how the wave would change along x and y, okay. So if you were to sketch this solution, how it would look, okay, as a function of say along x and along y. So let us say this is x, this is y, the width of the waveguide is a and the height of the waveguide is b, right. What would be the electric field component Ez? Ez would unfortunately be going away from the page, right. So it would be coming away from the page. Use your right hand rule to check that x cross y would be coming towards out of this particular page, okay. So we will not be able to just draw a line or something, we will have to mention them by dots and crosses. So if you have dot, that would correspond to field coming out and that would be along the plus z direction, and a cross would be, in my notation, that would be going in, so which means that it would be minus z. What would be at the walls? See, look at the walls are at x equal to 0, x equal to a, y equal to 0 and y equal to B. These are the 4 walls of the waveguide that we have. Of course, the wave actually propagates along z direction, right. So, in this particular case, what would be the electric field at x equal to 0? It has to be 0 because this is Ez, and Ez would be tangential to the wall, and that is also given out by this expression, right. So, substitute x equal to 0 or x equal to a, the electric field component will be 0 here. Similarly, at y equal to 0 and y equal to b, the electric field will also be equal to 0, right. So, you will not have any components here, you will not have any components here. Along x, you will have a component which would be going as sine, and it would do 1/2 of the variation, right. This would be essentially sine of pi x by a. Remember, all the field components will have to be directed out of the page, right. What would happen to sine pi y by b? Well, in this case, if you go like this, you will see that the field components have to be 0 in the middle, and then they have to be maximum here at the center, right. So, if you combine these two facts, you would be able to write down the mode, okay. So, let me write down the mode here, this is the mode, okay. So, you will have electric field component going to 0 there, and then at any point you have electric field Ez and Ey. We are trying to plot for the TM11 case, so it would look like, and in the center you would have a maximum electric field, and on here you would have a minimum electric field, right. So, at the center you will have maximum electric field, at the points here you would have minimum electric field. So, it would go to 0 here, and at x equal to a it would go to 0 again. So, if you just go slightly beyond here, you will have density of electric fields that would be increasing. So, here you can see that the density is maximum, okay, not really nicely drawing them. There is a slightly different way of drawing the fields. This is just the Ez components which we have drawn. Of course, if I were to include Ex and Ey, the picture would look quite different, okay. So, there would be density of the fields which are maximum. So, I should have actually indicated that by maybe I can draw something like this, okay. So, let me draw it in this fashion. Okay, and then start putting in the dots here, okay. Again, here I should have maximum dots, and then here I should go, see, along y also I should have minimal dots here, and then there is maximum over here, and then you go to minimum. So, if you plot the dots here, this is how you would obtain, okay. These are just the Ez plots. So, you might want to actually try out this way of plotting by taking a piece of pencil and paper, okay, and then nicely rubbing off all the lines that I have drawn here, okay, in the center. These are the ones that are not required, but you should get the sense of an idea that electric field lines are crowding at the center, and then they would be very thinning out, or they are thinning out at the waveguide walls, okay. So, there is very thick electric field component Ez here, whereas this component keeps on reducing as you go at the outer cases, right. So, this is for Ex. However, if you want to draw Ex and Ey at a given z plane, the plot would look slightly different, okay. So, given this Ex and Ey for the TM11 case, the plot would actually look this way, because you remember, although Ez actually goes to 0, whereas the components Ex and Ey are dependent on del Ez by del x or del Ez by del y, and therefore they will not go to 0, they will actually go to maximum, okay. So, because of that reason, the electric field lines would go to their maximum, right, at the waveguide walls when you are plotting Ex and Ey, and at the center they would be minimum, okay. So, at the center they would be minimum, and they would look something like this, okay. So, you will actually have a field lines that are going around in this way, right. So, there would be field lines here like this, okay, slightly onto the curved side. What would happen to the magnetic field lines? Well, magnetic field lines will always have to form a loop, and we can see that the field lines here, there wouldn't be, at the center it would be very small, okay. So, at the center I am actually not plotting like this. So it would be in this way. Okay. So let me remove this center line as well. Okay. Alright, so this we have removed the center. So this is how electric field lines would look. The electric field lines does not have any value at the center, because if you remember, that becomes cos, and then in the middle there would be a symmetry, and therefore there won't be any electric field lines over here. Whereas the magnetic field lines will have to curl around, and again the curling would be maximum here, okay, and then it would thin out as you go to the waveguide walls. Now at the waveguide walls they actually don't go to 0, remember, because of the continuity of the surface current, these H components would actually leave some waveguide wall currents. Okay, so this is how the electric field patterns would look for a TM11 case. Sometimes it is also necessary to open up along the waveguide wall, okay, along the direction of the wave propagation, to see how the waveguides would look. We know that because of cos omega t minus beta z, and we are really looking at omega t equal to a particular constant. So let us say omega t is equal to 0. So as you go along the z direction, it has to be in the form of a cosine wave, right. So it would be maximum here, you know, the field lines are all crowding up here, they would start to thin out. Okay, so let us say these are the way in which the field lines are increasing. Okay, they would then thin out like this, you know, it's a cosine waveform, it would go like that, right. And then what would happen after a certain distance, which is lambda by 2, they would start to reverse their directions, right. So they would reverse, and then they would go to maximum again, right. So this is what a cosine waveform would look along the waveguide direction. Okay, so along the z direction, this is how the waveguide would look. Okay, I mean the electric field lines would look as you go along the direction of the waveguide. Okay, similarly one can plot other modes. We are not going to do that one here. You can look up the pictures of the modes for other higher order modes. Let us not do that one, but rather what I am interested at this point would be to try and show you how the magnetic field lines would give rise to a certain surface current. Okay, so let us obtain the surface current, because surface current will determine, for an imperfect conductor, surface current is required in order to find out how much power is being lost because of the conduction, right. If you remember our discussion on skin depth, we wrote something like this, right. The power dissipation per unit area was something that was proportional to magnitude of Ht square, where Ht was the transverse component for the corresponding conducting surface, right. So it was essentially the power lost being proportional to Ht, which was in turn proportional to the current square that we had. So once I know the surface current, okay, in terms of Ht, then I can find out what would be the power that is being lost, or if I know the magnetic field component Hz, then directly I can find out what is the power being lost. Okay, so it is because of this imperfect conductor that a certain surface current is induced, and this surface current that is induced will result in heating up of the wall in the form of, you know, power dissipation. Okay, so let us try to find the surface current for TM modes. Okay, we don't have to specify what is TM of Mn, so let us find surface current for TM modes, and we know the result already, in the sense that we know the relationship between surface current and the magnetic field component, right. So the magnetic field component must be evaluated at the surface, and then you take the cross product of n, the normal to the waveguide wall pointing inwards into the waveguide, times Hs. Okay, so let us, we have 4 walls here. So one wall is at x equal to 0 and the other is at x equal to a. We have one wall y equal to 0 and y equal to b. So where will the directions of the normal be pointing? So for the n x equal to 0 wall, the direction will be along x direction, right. So the normal is along x direction, whereas for x equal to a wall, the direction of the normal will be along minus x direction. Similarly for y equal to 0, it would be along the y direction, at y equal to b it would be along minus y direction. Okay, so once you know these direction normals, then you can find out the surface current. Let us do it for the x equal to 0 wall, and because of symmetry the same expression would be there for x equal to a wall. If you do it for the y equal to 0 wall, if you find out the surface current for y equal to 0 wall, it would essentially be the same for y equal to b because of symmetry. So out of 4 components you need to evaluate only 2 components. I will do one more thing, I will evaluate only one component and leave the other component, evaluation of the surface current at the wall y equal to 0 and y equal to b, as an exercise for you. Okay, so you have Js at x equal to 0 wall given by x hat cross the magnetic field at that point. Now what are the magnetic field components? You have x hat hx, that is you have hx and hy. So you have x hat hx plus y hat hy are the two components of the magnetic fields. There is no hz component because of TM mode condition, and when you take x cross x, the result will be 0, x cross y, the result will be along z direction, and then you need to substitute for the value of hy. Okay, so I will not solve this one, but I will not go through in detail, but I will just recall the value of hy. You have to probably show this one as an exercise by following the last module, wherein we derived Ez and also indicated what forms for hy, hx, ex and ey would be. So you have hy, which is the component of the magnetic field, the transverse component of the magnetic field, which must be evaluated at the surface. First let us look at hy itself. The expression for hy as a function of x and z will be having some constants. Let us just write down the constants. It is your this one to actually prove that these are the constants that get multiplied to this one. Okay, and because of the differentiation of Ez with respect to y, there would be n pi by b, that is coming out here. The x dependence is still cos m pi x by a, whereas the dependence for y will become sine, it would be n pi y by b. There is also e to the power minus gamma z as the dependence on z direction. Okay, of course gamma must also be written with its subscript gamma mn. Okay, so this is your hy phasor. Now you evaluate the phasor at x equal to 0 and at y equal to 0. So if you evaluate this phasor at x equal to 0, what do you get? You will see here that this is, you will have m pi by a. So you can actually find out this component from the previous method that we discussed in the previous module. Hy evaluated at x equal to 0 will give you minus E0 j omega epsilon divided by h square mn. I do hope that you remember what is h square. It was related to gamma and omega. And x equal to 0, cos of 0 will be 1. So you just get sine of n pi y by b, right, e to the power minus gamma mn of z. This is the surface current that would be present at x equal to 0. The surface current shows a dependence along sine. It shows a dependence on sine as well as it shows a dependence along, this needs to be multiplied by m pi by a. It also shows a dependence along the mode order itself. So m and n values determine how much is the surface current. Again you cannot have m equal to 0, n equal to 0, because then there won't be any surface current, and moreover m equal to 0, n equal to 0 is not the correct solution. For the fundamental TM11 case, n will be equal to 1, m will be equal to 1, and whatever the expression that you obtain is the surface current. Let us close our discussion on TM waves and then proceed to what we call as TE modes inside the waveguide.